Now we will talk about a few more results from cyclic group, and we will do not going to the proof of the results because the proof are not in your course. So we just only discuss about these two results. So from that two results you may get some MCQ type problems in your exam. So let me start talking about the results. So here is the results 2. It says that, so here we are first talking about the results 2. So it says that if we have a G be a finite cyclic group, so it says that G finite means the group is finite, so G contain only finitely many elements, that's why it's a finite. So its G compositions is G is a group which is finite cyclic group. So it's a finite group as well as a cyclic group generated by the elements A. So G is generated by an elements A of the group. So A is an elements of the group and G is generated by that elements A. So then it says that order of G is n, so the group with n number of elements, order of G means the group has n number of elements if and only if order of the elements A is equals to n. So which means that if G contains, so order of G, so it means that if order of G is n, which means G contains n elements. So G have only n distinct elements. So if G contain n distinct elements and G is a cyclic group generated by the elements A, then it says that the elements A has order n. So this implies, this results will imply, if order of G is n, so and G is cyclic generated by A, then this must imply that order of A is n, which means that A to the power n equal to the identity elements of, so let me write the identity element E. So A to the power n will be the identity elements E of the group G. Okay, so if we have the order of the group G, order of the G is n, which means G contain n elements, then if G generated by the elements A, then it's definitely, you can be sure that order of A will be n, which means A to the power n will be the identity elements. So so in that case G contains only this type of elements. So G, we have the elements, so G is basically generated by A, means is the collection of all A to the power n. So remember that n belongs to the elements Z. So remember, the very careful, here we are talking about a particular n. So instead of n, just I want to write, do not be confused. So A to the power k, k is n integers. So when the value of k will be n, you will find that A to the power n. So G contains all the elements of the form A to the power 0, A to the power 1, A square. In this way, A to the power n. After A to the power n, we will get A to the power n plus 1, which is A to the power n composition with A. So we get E compose A. So we get the elements A. So all elements after A to the power n plus 1 elements will going to be repeated in cyclic form. So G contains only these n elements. So is the identity elements, sorry, A to the power n is E. So A to the power 0 is also E. So we do not have to write A to the power 0 and A to the power n both at a time. So what we're going to do, instead of both that two, we're going to write E, the identity elements. So G contain the elements E, A square, in this way up to A to the power n minus 1. So if G is a cyclic group generated by A and order of G is n, then order of A will be n, and in this case we can write in this form. So in the results also, not only the result says in this way, results also going a further step. So it says that, so let me write that first, let me erase that first and discuss the results. So it goes a few steps further and says that, so it says that if G is a group and G is a finite group generated by the elements A, and it says that the elements A has order n. If the order of the elements A is n, then it says that this it will be implied that order of G also going to be equals to n. So that's the another way. So if and only it means order of G is n, imply that order of A will be n, and also order of A is n, imply the order of the elements G also going to be n. So it's both way is true. So order of G and order of A will be the same. So in one way to say that if G is a finite cyclic group generated by the elements A, then order of the group will be same with order of the elements that by the group generated. So order of the group G will be same with, so remember that in a finite cyclic group, in so this is one way to say, in a finite cyclic group, order of the group is same with the order of its generator, same with the order of its generator. That's a very important results. So it says that order of the group will be same with the order of its generator. So that means if we find a group G with n elements, so here is a very important observation. We can find that if we find a group, so remember the observation. So first observation is, it says that in a finite cyclic group, order of the group is same with the order of its generator. So here from that we can observe a few more things, that remember the observation. So here is the observation. So it says that if G is a finite group, with n elements, so that means order of G is n. So order of G is n. Now if we find if no elements of G is of order n, so if no elements of G is of order n, so if no elements of G is of order n, so we do not find any elements of G which is of order n, then you definitely be sure that G is not a cyclic group, because in a cyclic group order of G have to be same with order of its some elements of the generated by the group. So you definitely be sure if we find no elements which is of order n, which is not equal to the order of the group, then you definitely be sure that G is not a cyclic group. Then G is not a cyclic group. Be very clear about their statements. If G is a finite group with n elements, so order of G is n. If we find no elements of G is of order n, then it's definitely be sure that G is not a cyclic group. So from these results we get this observation. So it's, if we do not find elements of G which is of or same with the order of the group, then you definitely be sure it is not a cyclic group, because if it is cyclic, then the group generated by an elements and the elements from the group G and the element order of A have to be same with the order of G, because if I do not find any elements, such elements for this equality is hold, so D is not definitely equals to some elements generated by some elements, so this is not a cyclic group. So this is one of the very important observations. So I just want to say one more thing about the results. So the above results, so let me erase that first. So they are very important results in group theory. So remember this results, it will maybe work for you in future, not now but maybe work for you in future. So the above results says that is a finite cyclic group, which means the order of G is some positive integer n. So I want to say you that, I want to inform you that instead of finite cyclic group, if the order of G is infinite, which means if G is an infinite cyclic group, the above result is still true. So we just want to let G be an infinite cyclic group generated by A, then is definitely for sure that order of A will be infinite. Then order of A is infinite. So order of A is not finite. So we will not find, which means we will not find any positive integer n, so that a to the power n will be equals to E. So order of A infinite means we will not able to find any such n. We will not able to find any such n so that a to the power n have to be equals with the identity elements of the group. So we will not find any such elements. So if G is an infinite cyclic group generated by A, the result still hold, and the converse of the result is still hold, which means that if G is a group generated by the elements A, and if order of A is infinite, then G is an infinite group. If G is generated by A and order of A is infinite and G is a cyclic group, then definitely for sure that G is an infinite group and G will be equals to a to the power n, and n belongs to the set of integers, and none of a to the power n will be equals to the identity elements. None of a to the power n will be equals to the identity elements except a to the power 0. We assume that a to the power 0 is the identity elements. So that's the results 2. Okay, next discuss about the results 3. So let me first erase this part and discuss the results 3. So here is the results 3. Before that, let me erase the above part. So it says that results 3, it says that a finite group G of order n is cyclic. So our finite group G is cyclic. So it says that G is a finite group and G is a cyclic if and only if there exists an elements B in the group G such that order of B equals to n. So in the above results, what's the difference between these results and the above results 2? So in the above result, it is provided that the group is cyclic and order of G is, we are talking about the order of the elements generated by the group and order of the group itself. But here it says that the order of G is finite. This is given, and it's given the order of G is n. It's it's the given. In evaporazole it's not given. Evaporazole is given that's finite and cyclic. So here is only given that's finite. Then it says that G is cyclic if and only if, so G is cyclic. We can say that G is a cyclic group if we can find an element B in the group such that order of B is equals to n. If we can find an element, so it's a very strong results. So it says that if we can find an n elements, if we can find an elements B in the group, show that order of B is equals to the order of the group G, then is definitely sure that the G is a cyclic group. So is very important. So let me write them down for you. So it says that, so let me write that down, that G is a cyclic group. So G is a finite. So I am discussing over here. So G is a finite group, and order of G is given that n. So the result says that G is cyclic. So G is cyclic group if we can find, so if cyclics imply and implied by, which means we'll obviously definitely find an element B belongs to a G such that order of B will be n. So that means in the above results it is given that G is generated by the elements A. Here nothing is says some that it is only says that order of G is n, and if cyclic that means G will be generated by some elements. The elements is not provided here, but it says that we will definitely find an elements B and whose order will be equals to n. And not only that, if we find an elements B, if its order is same with the order of the group, then G is definitely equals to a finite cyclic group. So we will discuss the results by taking more and more example. So let me give you some example to verify the above results 3. So here is an example. So we are taking the example. So let's take the group G is the group Z4. So Z4 is the collection of all modular class 0 bar, 1 bar, 2 bar, 3 bar. So modular class, so residual class of module 4, and we know that Z4 class is a group. Now what about the order of the elements 3? So let's check. So what about the order of the elements 3? So what is 3 bar? 3 bar 1 times. So 1 times 3 bar is 3 bar. So if I add 3 bar 2 times, so what means 2 into 3 bar is 3 bar plus 3 bar, which is 6 bar. Now if divided 6 by 4, we get 2 bar. So next 3 into 3 bar, we get 3 times, add 3 times 3 bar, so we get 9 bar. If I divided 9 by 4, we get remainder 1, so 9 bar is equals to 1 bar. And now 4 into 3 bar, which is addition of 3 bar 4 times, so after that we get 12 bar, and if I divided 12 by 4, we get the 0 bar, remainder 0, so it's equals to 0 bar. So you can see that clearly after taking 4 times addition of 3, so we get 0 bar. So order of 3 definitely is equals to 4. So now group has elements, 4 elements, so order of elements, order of 3 is same as order of the group. So let me erase that first. So order of 3 is same as order of the group. So from the results 3 we can say that Z4 class is a cyclic group. So this is one of the application of the results. So it's a cyclic group. So let me give you another example. So here this is one of the examples. So let me give you another example. So let me first erase this example. So here is another example. So first let me erase this first. So we know that the group G contain 1 minus 1 I and minus I, where the I square equals to minus 1, and we know that 1 is the identity elements of the group. So 1 is the identity elements of the group when we are talking the group by taking under multiplication. The composition is multiplication, so G under multiplication is a group, and 1 is the identity elements of the group. And we know that for sure what is I to the power 0. I to the power 0 is 1. So next, I to the power 0 is not a positive integer, so 0 is not the order of the elements I. So what is I to the power 1, which is I squared, which is minus 1, still not get the identity elements. I cube is minus I, still not get the identity elements. I to the power 4, we get 1, so we get the identity elements of the group. So order of I is definitely equals to 4, and group has 4 elements, so order of the group is 4. So we get an elements I, which is of order of the group. So G is a cyclic group. So G is a cyclic group. So this is another application of the above results of that group is cyclic. So this is the application of the results that a finite group G is of order n is cyclic if and only if there exists an elements B which is of order n. I want to be one step further to say you that, so in this case actually G will be generated by the elements B. So remember that it is one step further, G will be generated by the elements E. I think you understand the results. If you do not understand the results, that comment me below in which steps you just miss out the results, and just comment that below. We can discuss about this, or you can contact me in another way that's provided by our university. So thank you for watching. We'll see you in our next class, in which we will talk about a very important theorem of group theory, about the Lagrange's theorems. So before that, thank you and stay healthy. Goodbye.